Okay. So this is just a fake class to practice. You guys ready? All right. So today we're going to talk about molecular shapes. So molecules have a particular shape mostly because of electrons repelling each other. So that's the big idea. Electrons repel, not repel. Electrons repel each other. And since they repel each other, they want to spread out. And that spreading out basically determines the shape of the molecule. So this is called the VSEPR model. And VSEPR comes from valence, shell, electron, pair, repulsion. VSEPR. So in order to figure this out, we first need to review a little bit about drawing Lewis dot structures. So let's look at an example that you might remember. Let's look at carbon dioxide. So I want you to go into your own channels right now and draw the Lewis dot structure. And then I'll come around to those channels and have your answer on your whiteboard. And when I get there, then you can hold it up and we can check in and see how we're doing. All right, Harold and Lizzie, you guys made progress on this? All right, yeah, Lizzie, I can see yours. Harold, can you back up a little? Right on. Okay, looks good. All right, I'll see you guys back in the general meeting. I'm going to check another group, so try and be back there in 10 seconds. And I'm lying, I'm not really going to check another group. But that's what I might say. All right, you guys did well. So carbon dioxide, when we draw the structure, as most of you figured out or remembered, you've got two double bonds. So it ends up looking something like this. Now, when we're determining the shape, the important thing to think about is what's going on around the center atom, so the carbon. So if you look, we've got a double bond to the left onto oxygen, a double bond to the right onto oxygen. Now, even though this double bond is two pairs of electrons, it really goes just towards one place, towards the oxygen atom. And obviously the same thing on the right. So this whole thing, this whole connected atom, you can think of as one group of electrons. Even though there's a nucleus inside there, there's a big electron cloud. And then this is another big electron cloud. So one way to think about it is if you had the center atom as a ball, and then it's connected with sticks to other balls, would look something like this. Or we can even use our model kits. So let's say I've got this gray atom is my carbon, and then I connect one oxygen atom to it. And then if I want to connect the other oxygen atom, now remember there's electron cloud around the oxygen, and so it wouldn't go like this, right? Because electrons repel each other, and so they wouldn't want to be this close. They get as far apart as they possibly can, and so then it's going to instead spread out, spread out, spread out, spread out. Where can it go to be as far away as possible? And it ends up being 180 degrees, right? So that's the model. And just FYI, as you're using your model kit, not all of the central atoms can actually allow for 180 degrees. So the gray one works, but if you chose one of the black ones, it might not even have 180 degrees as an option. So you might have to switch it up a little bit. So what I want you guys to do is, again, in your channels, go ahead and put together some models for a couple of other molecules. But wait, let me back up a second. So we're going to use a language of electron group when we build the VSEPR models. An electron group could either be a bonded atom, like we have with oxygen and carbon dioxide, and it doesn't matter, this bond could be single, could be double, could be triple, that's still one group. Okay, or it could be a lone pair. Okay, a lone pair is also a pair of electrons that need their own space, and they're going to repel the other electrons. So let's look at a couple of examples. So you might remember there's an exception to the octet rule, group 3 halides. So for example, boron trifluoride. This is the Lewis dot structure, and we don't have a complete octet. We only have 2, 4, 6 on the boron. So let me ask, see if you guys are paying attention. How many electron groups would be on this boron trifluoride? How about you, Lizzie? 3. Right, 3 groups. So when you build your model, you'll want to think of the boron as the central atom, and then the fluorines being 3 groups around that. And then another example that we're going to do is NH3. Lewis dot structure for this, which is ammonia, has the 3 atoms, and then it also has a lone pair. So how many total groups is that, Harold? Yeah, that's going to be 4 groups, because you got the 3 atoms, and then you got the lone pair. All right. So actually, I'm kind of changing my mind here. I'm going to do this as a Socrative quiz. So let me share my screen here a minute. Go ahead and build your models and look at the angles while I bring up a Socrative quiz. Okay, I've almost got the quiz ready. Hopefully you've got your models built. All right. And then let me share my screen here, and we'll see how you guys do on the Socrative quiz. So remember, Calvin Chem is our room name. So go ahead and log in when you can. Oh, shoot. Never mind. I have to share my screen in a different way here. Stop sharing. Share again. Okay, how about this? All right, let's see how we did. Yes, there are two double bonds. Oh, that was the wrong question. Let me do this one. This is the one I meant to do. Trying to resize screen. Okay, how do we do? All right, right. So for the boron trifluoride, it's 120 degrees. Let's look at the ammonia. Yes, for the ammonia, it's 109.5 degrees. All right. I'm going to stop sharing my screen, and then I'd like to have you guys just go ahead and hold up your models. So for the boron trifluoride, Lizzie, can you show us what you got? Okay. So everybody thought it was 120 degrees, so you must have too. So how did you figure that out? Very good. All right. And then how about the four groups? Harold, can you show us your model? Okay. Nice. Okay. And you thought 109.5. Can you kind of talk us through your logic there? All right. All right. Thank you very much, guys. That's it for our fake lesson.